What if we now go to 3 dimensions? Or, well, we're going to have rotation on a sphere. We're still going to hold the radial distance constant, but now we're going to let it move. Our particle can move such that both the azimuthal angle and the polar angle, or the colatitude, as it's also known, theta, both of those can change. So it's what we call a particle on a sphere of a fixed radius. All right. But the procedure is the same. Set up the Schrödinger equation, and then we have to define our Hamiltonian. The Hamiltonian, we're going to have to use that full Legendrian in there. And first, it looks pretty daunting. We got a second order differential equation. The best way to solve a second order differential equation is to look up somebody who's already solved one of these problems, right? And ask them what the solution is. So we need a Belgian monk. And then we need to get our equation into the form of an equation that's been previously solved. How can we do that? Well, let's use a trick known as the separation of variables and separate our total wave function into we've got an eye on trying to solve the hydrogen atom problem later, and this is how we're going to do it. We're going to separate out one bit into a radial function. That should be easy to do because right now we're fixing everything on a sphere of constant radius. So this is just going to be a constant in our problem right now. And then there's going to be some function of these two angular variables. All right, so we're going to substitute this into our Schrödinger equation. And then what we need to try to do is to somehow separate this into terms that only depend on r, or only the angular variables. And this can be done if we divide through by r times y and then multiply by this factor minus 2mr squared over 2h bar squared. And then we will end up with separated variables, terms that only depend on r, and another set of terms that only depend on the angular variables theta and phi. All right, so that's what we're going to do. And what we find is that indeed we can separate this into one term that only depends on r and another term that only depends on theta and phi. And this is a really cool trick right now. We've got two terms that depend on different variables, and they add up to a constant, 0. The only way they can always add up to 0 is if this term is equal to a constant and the second term is equal to a constant which is the negative of that constant. Two terms which depend on different variables can only sum to 0 if they both are equal to constants, and one constant is the negative of the other constant. Okay, so that means we can concentrate just on the angular term right now. It must be equal to a constant, and we are going to very suggestively say that this constant is equal to minus L times L plus 1. That should sound familiar already, right? Because we're not going to lose any generality here if we call it L times L plus 1, because if this term is a constant and L, we can also make this a constant. It's going to turn out L must be an integer. Um, and then if we put an integer in there, boom, we also get a constant. All right. That radial term, we're going to put it to the side. When we go back to solve the hydrogen atom, we'll have to actually deal with it. Right now, we're just saying it's a constant, right? We fixed the value of r, so it's just a constant. All right. So this equation has well-known solutions if, again, we get it into a form that's already been solved by somebody else. And we can, again, use this trick, right? What we want to do now is multiply both sides of that equation by y sine squared theta. And if we do so, right, we get it into a form that's well known from classical electrodynamics. This is the Laplace equation, which has already been solved. We can use the equations of the solutions of the Laplace equation here to solve this problem. All right, so we've got a left-hand side and a right-hand side. And We've got one term over here that only depends on theta, one term that only depends on phi. Oh, very nice, because then we could again introduce separation of variables and introduce this substitution, collect up two terms, and what we find is we end up with one term that only depends on theta, one term that only depends on phi, and again, two terms of different variables can only add up to zero if one term is equal to a constant and the other term is equal to the negative of that constant. Again, we're going to suggestively call this constant m sub l squared. And oh, that one looks familiar. We've already had that problem. Indeed, the particle in a ring has the same solution. It's the same solution here. E to the I m sub l phi will be the solution for this capital phi problem up here. And just as before, the solution is going to be m sub l has to be quantized in order for this function to be single valued, and therefore m sub l must take on integer values starting at 0 and being plus minus 1, and so on. However, now there's an upper limit to what the m sub l values can be, and in fact, they're constrained by this equation up here, the theta equation. Again, a little more complex, but its solution is well known from electrodynamics. And it turns out that we are going to use these well-known associated Legendre functions, and that there's going to be one quantum number associated with those, the L quantum number. L must be a non-negative integer, that it starts at 0 and goes 1, 2, etc. M sub L can be plus or minus, but it's got values that are constrained by the value of L. So L sort of has priority, comes first, and then M sub L can take on values from L to minus L in unit steps. All right. Very good. Then, of course, we want to make a good wave function. Our wave function here should be normalized, so we integrate over all angular space. We should get a value of 1. That we can do, and it generates a set of functions that are known as the YLMs, or alternatively, the spherical harmonics. And you can see they're just a normalization constant times a function of theta and phi. You know these functions, or at least you know the shapes of these functions. They're familiar to you. These functions, the YLMs, are responsible for the characteristic shapes of orbitals. So some of these you've already seen, right? An s orbital, a pz orbital, a dz squared, an f orbital. Those ones, boom, just exactly what you expect. Now, to get the other components that you're used to, p, x, and y, you're going to have to make linear combinations of these other solutions here. But notice what's happening, right? L equals 0, there's only an m equals 0. L equals 1, we get plus 1, 0, or minus 1. So there are increasing numbers of m sub L values for each value of L. In fact, there are 2L plus 1 values of m sub L for each value of L. All right, so we quantized the system, the particle on a sphere system. We quantized it along two angular coordinates, theta and phi. And guess what? We got two quantum numbers. L is the azimuthal quantum number. M sub L is the magnetic quantum number. And the energy we're going to find out is determined by the L value. And the shapes are related to M sub L. All right. That m sub L, right? It denotes the projection of angular momentum along the z-axis, and they're constrained to certain values. So when you've got an angular momentum, it can't just point anywhere in space. Once you have a well-defined z-axis, it can only take on certain values, right? The z projection is defined. The length of the vector is well defined. That's related to L, and its projection onto the z-axis is well defined. That's related to m sub L. So one way to think about it is this precession model here, right? That you've got a vector, a fixed length, and it's rotating about the z-axis. The component along the z-axis stays constant. The length of the vector stays constant, but the x and y values, if we're looking down from the top, the x and y values are constantly changing, keeping the length of the vector the same and the projection on the z-axis the same. All right, so for particle in a sphere, we solve the Schrodinger equation. The Schrodinger equation then has quantized values of energy. The energy only depends on the L value, right? The L value determines the energy, but there are two L plus one M sub L values. Those determine the projections of the angular momentum along the Z axis. All right. So the energy doesn't depend on M sub L, it only depends on L. For each value of L, there are two L plus one levels at the same energy. In other words, we call that degenerate sublevels. Two L plus one degenerate sublevels. Sublevels are all at the same value of energy. All right, and they correspond to the two L plus one different ways that the vector can point in space.